Okay, so far we've just described what we see. We have done kinematics. We have discovered that the planets orbit along elliptical orbits. Now the question is, what can we do to use the laws of physics to understand how this happens? The law of physics that applies, of course, is gravity. And the first question you can ask is, wait, gravity is supposed to attract these galaxies or these dust flakes to each other. Why is it that they're moving apart? Well, in some sense, this is similar to the question of, look, gravity attracts this roll of tape to the ground. Why is it moving up? Well, it was moving up because right outside the screen, my hand threw it up. At some point, we will be very interested in going deep into the past of the universe and trying to understand what it was that initiated this expansion. But at the moment, we're observing it and we're trying to apply the law of gravity to understand what we expect it to have looked like in the past and what we expect it to look like in the future. And we'll do this using Newtonian gravity. As I said, we'll leave general relativity for later discussion. We will see that many of our considerations from Newtonian gravity carry over. This will allow us to sort of address some of the conceptual issues in a technically simpler version using Newtonian gravity. So back to our expanding shells of dust. Here's our favorite shell. Here it is at time d0. Here it is in the past. It was closer to us. And what we're going to do is compute the energy of this object. And at time d0, at time 0, it's at distance d0. In the past, it was closer. And this shell is moving. And the speed at which it is moving, we computed a couple of clips ago. We said that v at any time t is h at time t times d at time t. And we also said that if you want, h of t is a dot, the rate of change of a at time t, divided by a of t times d of t. And if you want, again, you can collect this into d0. And so here are two ways to write the speed or the velocity with which the dust in the shell is receding from us at any time t. Now, we have a moving shell. Remember that recessional motion is the only motion of the shell, and we're working in the context of Newtonian physics, so we can compute the kinetic energy of this object. We have a velocity. We plug it into our kinetic energy formula, and here is the version that I want to use for the kinetic energy of the motion of the shell as it expands. Now, in addition to its kinetic energy, there's some conservation law, the conservation of energy. And the conservation of energy in our Newtonian framework is going to be governed by Newtonian gravity. Now, what does Newtonian gravity tell us about the motion of this shell? I have to be a little bit careful. The shell lives inside a uniform dust-filled universe. Now, there are two approaches to understanding what gravity does to an object in a uniform dust-filled universe. One approach would say, well, because of symmetry, the force of gravity on any object in the universe is zero, because there's as much stuff to its right as there is to its left. But here's an alternative description. Because of symmetry, all of the material outside the shell exerts zero force on the particles in the shell because they are inside a spherically symmetric distribution, whereas all of the material inside the shell exerts some gravitational effect on the shell as though all the mass inside were concentrated in the center. Which of these is true? It turns out that this is a subtlety involving the very distant parts of the universe. We're going to assume the latter. In the context of the general relativistic theory, we won't have to make such assumptions. It will actually be true. Here, I am going to, if you wish, you can assume that actually this is not an infinite universe. It's just way larger than anything we've ever seen. So if a trillion light years away is the edge of this universe, then you can imagine now we have a spherically symmetric distribution, a trillion light years across, and we're looking a few billion light years from its center, where we can assume that every point is at the same distance from the edge. So with that caveat in mind, the potential energy of this shell is easy to write. The potential energy is given by, U, is given by minus G times M divided by d0, or at any time t, d of t. Now, M, of course, is the mass of the shell, And we saw the mass of the shell is conserved. It's the same shell that's expanding. At any time, I'm going to be talking about all of the dust in that shell. So m, little m, is time independent. What about big M, the mass contained inside the shell? Well, that too is time independent because, of course, there's no creation of material in here. So I can compute this at any time that I wish. But how do I compute this? Well, M is given by the volume of the sphere of dust contained by the shell, which is 4 pi over 3 d of t cubed, if I compute it at time t. And I agree that big M is a constant, times the density at time t. And of course, since this goes like 8 of t to the minus 3, this goes like a of t, we agree that M is time independent, but it's in this form that I want to plug it into here and see that I get minus 4 pi g over 3 times m. And then m brings a d of t cubed. I see a rho of t times d of t squared. This is the expression that I want to use for the potential energy. So let me write it cleanly. And here is my expression for the kinetic energy of the shell and the potential energy. And since there are no forces acting other than gravity, the total kinetic plus gravitational energy is conserved. So I can write an equation that gives me the total energy by adding these two, and I can extract from both of them a factor of m. Of course, everything is proportional to m. I extract the common factor of d squared, and I'll extract a 1/2 at the cost of putting an 8 pi g over 3 here instead of 4 pi g. And here I have the expression. This is the energy of the shell that I called the shell d0, which lies at this distance and then has some width. And of course, if you make the shell thicker, its mass gets bigger, and you're talking about more energy. There are some important things to notice about this expression. Fact number 1 is that if I factor out this d squared, I get an expression that looks like this. I'm going to also factor out the 2, so I take e and divide it by this common factor, and I get this answer. Now, the important thing about this way of writing it is that if you look at the right-hand side, it has quantities in it that are h squared, the square of the changing Hubble constant. It has the density, but it has nothing that tells you which shell you were talking about. The right-hand side is the same for every shell. Well, that means that the left-hand side, the ratio of the shell's energy to its mass times the square of its present distance at any time t, is a constant, which is why I called this epsilon. This epsilon is the same for all shells. Well, fine. So this is some constant that describes the motion. How does epsilon depend on t? Well, we know how epsilon depends on t because we know how E depends on t. How does E depend on t? Well, it does not. Energy is conserved. I did not write a t here because I know that over the course of, say, the expansion, the expanding shell will slow down, losing kinetic energy as it converts it into potential energy. We're familiar with this story. And so, since energy is conserved, this quantity epsilon depends neither on the choice of shell, nor on time. And in particular, what that tells me is that, E does not depend on time, so epsilon depends on time only through the time dependence of d squared. So I can write, in particular, that factoring out a common factor of d0 squared, I can say that epsilon, or some other quantity, epsilon prime, I should say, which is where epsilon prime is twice the energy of the shell, which is a time-independent thing, times m, times the square of where the distance the shell was at time 0, and then epsilon is the same thing divided by a squared, because d of t is d0 times a. So I take epsilon prime over a squared. Let me put that prime back where it belongs. And this epsilon prime is a quantity that is independent of time and of the shell, and this is some constant of the motion, and epsilon prime is given by this quantity. So this quantity is a constant, and over time, as rho, remember, changes, rho decreases. Since this is supposed to be a constant, this is negative, this is positive, h will decrease the expansion is going to slow. We're not surprised. Gravity is going to slow the expansion, and we can solve for this quantitatively in the following way. So remembering here, I'm going to recall what I called epsilon prime will now be called epsilon because it's too complicated to put in all the primes. I have this constant of the motion epsilon, and epsilon divided by a squared is this quantity. Now, remember that this epsilon prime was basically the energy divided by mass times d squared, and so the sign of epsilon is the same as the sign of E. Oh, but we know something about the sign of the total energy in gravitational motion. If epsilon is positive, then the energy is positive for every shell, and all the shells are unbound, so they're all going to continue moving out to infinity. They might slow down, but they will move out to infinity. The expansion is going to continue forever. If epsilon is negative for one shell, it is negative for all shells, and that means that all of the shells are bound, and this expansion will stop, and then gravity will pull everything back in. So this constant of the motion that we found, the ratio of the energy of a shell to the square of its present distance, is a distinguishing property, and we want to look at how it looks like. So motivated by this, we're going to say, imagine that this was our universe. This turns out to be not a terrible approximation to our universe. So in our universe, we can measure the Hubble constant, at least at current time, h0. We can measure, or try to measure, the total density of matter. And we can ask, is our universe going to continue to expand forever? Or will it stop expanding and contract under the force of gravity? This is a legitimate question, and we can answer it. To answer it, it pays to define at any time something I'll call the critical density. The critical density at any time is given by the Hubble constant at that time, divided by 8/3 pi g, and it is the density which, if you plug it into here, would correspond to epsilon equals 0. So the statement epsilon positive is the statement that the density is less than the critical density. The statement epsilon negative is the statement density is more than the critical density. And to make that even more stark, we're going to define a rescale density, omega, which is basically the ratio of rho, the density, the actual density, to the critical density determined by the current value of the Hubble constant. And in terms of this omega, we can factor out all of the 8 pi g and so on, and write an expression that says that a of t squared times the square of the Hubble constant times 1 minus omega, all of this becomes omega times h squared, and so a of t squared, h of t squared times 1 minus omega squared, omega is given by epsilon. Now how do we figure out epsilon? Well, measure today. We measure the Hubble constant. Remember, the inverse Hubble constant is about 13.8 billion years when we measure it today. Measure the density, compute the critical density from the Hubble constant, and decide whether our universe will expand forever or not. Now, given a particular value for omega, we can actually, this becomes, remembering that h is related to a by h is the rate of change of a divided by a. This becomes, and that rho is rho 0 times a to the minus 3, this becomes what we call a differential equation for the function a of t, and I can solve it. Now, we don't solve differential equations here, so I'm just going to tell you what the solutions are. In fact, I'm not even going to bother to write them until later. I'm just going to plot them. So let's see what the evolution of the universe looks like for various values of omega, and of course the interesting question is omega bigger than 1 or is omega less than 1? And what I've plotted here are 3 universes, all of which have h0 inverse equal to 13.8, I think I took, billion years. And here, as a function of time from the present, so the axis here is the present, at which I've plotted the scale factor of these universes as a function of time. And of course, for all of them, a at the present is set to 1, as it always is. The blue line corresponds to a universe with omega less than 1, the red line to a universe with omega equals 1, and the black line to a universe with omega bigger than 1, and as we see, in the case that omega is bigger than 1, the density is bigger than the critical density. All the shells are bound, the expansion will stop, and in a finite time, here about 70 billion years in the future, the universe will crunch down. Now, notice that all of these solutions have a time in the past when A was 0. Looking back, this is our prediction for the Hubble time, but notice that because of the nature of these solutions, because of the curvature of these solutions, the time in the past at which the universe was size 0, remember this is the part where you have to go back to understand who threw these galaxies up in the air, into space. Air is not where they're at. This time, if you look at the graph, is much less than the Hubble time. It's about 2/3 of the Hubble time in this particular case. So 2/3 of 14, about 8 billion years ago. If this were true, any of these models would predict that the universe is younger than the Milky Way, or the oldest globular cluster, certainly. And so we haven't found an actual model describing our universe, but it is heartening that we didn't get 6 million years. So we got the right order of magnitude just by replacing all of the stuff in the universe by dust. It's a pretty reasonable approximation, and it gives us a sense for how cosmological evolution is computed in a case where we can actually do the calculation. I had to solve the differential equation for you. If you're feeling energetic, you can actually do that yourself. Now, this is the story of all of these universes, and I want to turn that around and see what it tells us about what we would observe in our universe if we lived in one of these three universes. So what am I going to do is I'm going to read this graph sideways. Instead of reading it as giving the scale factor as a function of t, I'm going to imagine that I read it sideways and find the t at which the scale factor was something. Why do I want to do that? Well, because the scale factor is related to the redshift of objects observed at some time in the past. So I'm looking from here into the past. I'm now focusing on the left side of this graph, as a is 1 over 1 plus z. And if I know the time at which I had a particular scale factor, I know the time at which I had a particular redshift, from which I see a particular redshift. And if I know the time, then multiplying by c, I know the distance. So reading this graph sideways gives me the redshift distance relationship in the blue, the black, the red universe. The red universe is called critical because the density is equal to the critical density, and the blue universe is subcritical, and the black universe is supercritical. So I can look at these three universes, find what the redshift is for a given redshift, how far back in time I am looking, and I see that in none of these can I look much further than 10 billion years ago, because that's about the age of the universe that they predict. And I see that for all of the three of them, at small redshift, I see a linear relation between redshift and distance. Well, that's a poorly drawn straight line, but you see what I'm saying. And this straight line, of course, is the statement that the distance, which is c times the look-back time, I've made this the time from emission to the present, so I've flipped the time, the sign of the time, but c times the look-back time is, of course, supposed to be, the distance is supposed to be related, if I multiply it by h0 over c, so I cross this out and multiply it by h0, this is supposed to give me z, and so the straight line here is giving me, they all have the same slope because I arranged for all of them to have the same present Hubble constant of 1 over 13.8 billion years. So what we note is that in all of them in the past, the redshifts are too big. They all deviate to the right. If you look deep into the past, you find redshifts too big for a given distance, bigger than the redshifts predicted by the Hubble law. Does that make sense? Sure. Look back at where we came from, and you'll see that in the past, in all three cases, because expansion is slowing, in the past, galaxies were receding faster than they would have been had the expansion been at a constant rate. This deceleration of the expansion shows up as a deviation from the Hubble law to the right here to a larger redshift at a given distance, or smaller distance at a given redshift. That is the sign of slowing expansion. So we have a framework in which to look at our model and in which to look at our real universe. So let's take a first quick peek. What do we know? Well, we know the Hubble constant. Remember, it is such an important number that we parameterized our ignorance for years and years and years. by saying that it's on the order of 100 kilometers per second per megaparsec, and then we parameterized the ratio by this little number h, and recent data suggests that h is on the order of 0.71. That's not the most recent value, but it's good enough. And so from this, I can plug in, and you're more than invited to do the unit conversions, and find the critical density. And the critical density corresponds to 4 times 10 to the minus 28 kilos per meter cubed. That is on the order of about a quarter of a proton per meter cubed on average, is the density it would take, given this non-relativistic model, for our universe to be critical. And if there is more than 1/4 of a proton per meter cubed, then expansion will stop and the universe will contract again, which brings the important question: what is the density of matter in our universe? Are we going to continue to expand, or will we contract back? And our best data come from, well, what can we do? Well, we can count baryonic matter, normal matter, by looking at stars and galaxies and doing something called the light-mass ratio of various objects and counting how bright they are. And crucially, remember we have those core samples that quasars give us, which sample the intervening clouds of hydrogen over huge distances, including deep into the past. These are one of our best tools for estimating the density of hydrogen in the universe. Between all of these, we find that the density of all of the normal matter, all the baryons, all the protons, essentially, that comprise normal matter in the universe is a little less than 0.5% of what it would take to make the universe critical. Now, we know, of course, that this is not all of the mass in the universe. Most of the mass in the universe is in the form of dark matter. We've discovered that by looking at the rotation curves of galaxies and of clusters and at gravitational lensing. And so we have an estimate for what the ratio is of the two at different scales. We apply that, we add other measures, and our best estimate today is that the density of dark matter is such that when you add them up, you get about 1/4 of the critical density in the form of dark and baryonic matter. So you can use this to plug into the model. You notice that this is a model. Oh, we have a prediction. The universe will probably continue to expand forever, and it will slow down but never stop because the energies of all the shells in the universe are positive. We do not have a big crunch scenario, and we can use this value of omega to refine our estimate for the age of the universe to about 8 billion years. Well, that's not very good. Clearly, this model needs modification, but this is not bad for a first pass with Newtonian physics through the universe. And while the Newtonian approximation made our life simple, these roughly was the state of affairs as they were understood in, say, the late 1980s and early 1990s. We knew that the age of the universe seemed to be a little bit less than the ages of the oldest globular clusters, but we figured adjusting the constants would adjust things. We had a bit more of a problem with this measurement of omega. Theorists, for reasons that I hope to discuss later, maybe next week, had a strong bias towards the assumption that omega is probably 1. And 1/4 is very far off from 1, and so it brought the question of where is the missing matter. We hope to find it, but this is a pretty good description of at least this aspect of the state of cosmology in the 90s, and we'll see soon what has happened since. A lot.